Hello dear children, welcome to this crash course. We will discuss electromagnetic induction and AC. This is an important chapter. First, let's take up the concept discussion. Let's go through the important ideas and recap the important equations. Later, we'll solve some problems based on this. The basic idea of EMI and AC arises from the idea of change in flux. So, what is flux? What is magnetic flux? The first idea that we need to revise is the idea of magnetic flux. Magnetic flux is again very similar to the idea of electric flux, and we can write it as the dot product of magnetic field vector and area vector. For example, if we consider magnetic field lines to be represented like this, and if the area vector of this is along this direction, subtending an angle theta, then the flux is given by BA cos theta, theta being the angle between these two. If the magnetic field is, however, variable, for example, here is a surface under consideration, and the magnetic field is different at different points. For example, magnetic field representation is something like this. Magnetic field is different at different points on this. Then the magnetic flux over this entire surface is given by integral B dot dA, where dA is a small patch on this, and the area vector corresponding to this is dA, and the magnetic field at that point is B, and those two subtend an angle theta, and therefore the net flux is given by integral B dot dA. In the case of a uniform field, it is simply B dot A. In the case of a non-uniform field, it is integral B dot dA. By the way, this can also be written like this, B dA cos theta. So, whenever there is a change in flux, then there is an induced EMF set up linking that circuit, and this induced EMF or this process is known as electromagnetic induction. So, change in flux gives rise to an induced EMF, and this induced EMF may give rise to induced current if there is a closed loop. If there is a closed loop, it may even give rise to an induced current, and this process is known as electromagnetic induction. There are two basic laws describing electromagnetic induction. Let's just recap them. First is, it tells us, or say according to the first law, there is an induced EMF whenever there is a change in flux. There is an induced EMF whenever there is a change in flux. And the second is, the induced EMF is equal to, or the value of the induced EMF is equal to the rate at which the flux changes. So, rate of change of flux. So, these are the two basic laws. Now, if I take this induced EMF, it is actually given by minus d phi by dt. The negative sign is in accordance with energy conservation, which basically is represented by something known as Lenz Law. According to Lenz Law, the direction of the induced current is such that it tries to, oppose any change in flux. It tries to oppose any change in flux. So, according to Lenz Law, the direction of the induced EMF is such that it tries to oppose any change in flux. So, we have E is equal to minus d phi by dt, minus d phi divided by dt. Now, the flux being given by B A cos theta for one turn of the coil and NBA cos theta for n turns of the coil, the change in flux is perhaps due to change in number of turns or change in magnetic field, change in area, or probably change in theta, or any combination of them. Thus, if any one or more than one undergoes a change, then there is an induced EMF. So we may write perhaps E is equal to minus d by dt of flux. Flux is given by NAB cos theta. That means suppose area undergoes a change, then in such a case I need to write minus NB cos theta come outside and I have to write dA by dt. Or if magnetic field undergoes a change, then I need to write NA cos theta into dB divided by dt, etc. So all depending on the type of the change taking place, then the equation gets modified. So in every case, the induced EMF is given by the differential of this term NAB cos theta. But remember, there may be multiple variations also. For example, both A and B also probably they undergo change. In such cases, you need to consider the partial derivative. The induced current is given by induced EMF divided by resistance. Induced EMF divided by resistance. There is one more way of producing induced EMF. Let us see what is that. This is basically due to motion of a rod, conducting rod in a magnetic field. For example, if I consider a conducting rod of length L and let's assume that it is moving with a velocity v in a magnetic field B, then the induced EMF across its ends is given by E induced is equal to LVB, or this is LVB. But it is possible that these are not perpendicular to each other. So we should be a little careful here. The three parts are perpendicular to each other, or a better representation is induced EMF is equal to L into V cross B. This is basically L dot V cross B. So induced EMF is given by BLV. This can also be written as something like this. If you consider a specific case like this, there is a rod of length L, say, and if I consider this is the direction of V, and let's assume that the magnetic field is in a particular direction, say B, subtending an angle theta between them, then the induced EMF is given by LVB sin theta, theta being the angle between the direction of motion, that's direction of velocity, and that of the magnetic field. One of the important applications of this concept is a rotating rod. A rotating rod. If I consider a rod of length, say L, rotating in a magnetic field at a constant angular velocity omega, say in a magnetic field B, then between its ends A and B, the induced EMF is equal to half B omega L square, half B omega L square. Now you may ask which end is at a higher potential, which end is at a lower potential. Very simple. So in such cases, how to find out? So notice that V is in this direction, B is in this direction, and therefore the rotation happens in this direction and B is in the inward direction. So clearly the linear velocity of every part of the conductor is in the upward direction at this instant. Therefore, this end becomes positively charged, this end becomes negatively charged. This is as good as a cell whose polarities can be shown like this, half B omega L square. So half B omega L square is the induced EMF, and this end is positively this end is as good as positive terminal of the cell, the other end is as good as negative end of the or negative terminal of the cell. As an example, if I consider a coil whose spokes are like this, and let's assume that these are all metal rods, there is a metal ring, etc., and there is an inward magnetic field, and assume that this is rotating in this way, then between its center and any point on the periphery, any point on the circumference or periphery is given by the following idea. So observe that each rod is as good as an induced EMF of this kind. For example, this is the cell, and I got one more cell, and I got one more cell. Likewise, you can think of as many cells as the number of independent rods. But if you look at them, all of them are connected in parallel. Therefore, the induced EMF is simply given by half B omega L square. The induced EMF is given by half B omega L square. This process of induction may take place because of the change in flux in an outside coil or maybe inside a given coil. This actually introduces the idea of self-induction and mutual induction. Let us see what is that self-induction. When a current flowing through a coil is changed, the flux linking with its own windings change. And due to the changes in the linking flux with the coil, an induced EMF occurs. This is called as self-induced EMF. This induced EMF opposes the cause of the induction, and the property by virtue of which this takes place is known as self-inductance. This is described in terms of self-inductance, or say coefficient of self-inductance. Coefficient of self-inductance L is given by the flux linking with the coil divided by the current. Flux linking with the coil divided by the current. Therefore, I can write flux is equal to L into I, and the induced EMF because of this is given by minus d phi by dt, and therefore this becomes minus L di by dt. So I can define coefficient of self-inductance as induced EMF divided by the rate at which the current is changing. So this is basically the ratio of induced EMF to the rate at which the current is changing in the given coil. Remember, even though this is the expression, the self-inductance depends on two things. It depends on the dimensions of the given coil and the medium inside the coil. It is the property, it's basically geometrical property of a given coil. Just like resistors, resistance and capacitance, it's a geometrical property. The inductor or inductance is typically represented by this symbol. And these inductors can be connected in series or they can be connected in parallel. If we consider combination of inductors in series, for example L1, L2, etc., then this is equivalent to a single inductor whose inductance is given by L is equal to L1 plus L2 plus L3 and so on. In parallel combination, L1, L2, etc., and the inductance L is related to these by the reciprocal relation. 1 by L is equal to 1 by L1 plus 1 by L2 plus 1 by L3 plus and so on. So this is the relation as far as these are the relations for series and parallel combinations. Mutual inductance. In the case of mutual inductance, the change in one coil introduces or induces a current in the other coil. This is what is called as mutual induction. This is understood in terms of mutual inductance represented by the symbol M. Mutual inductance is the flux linked with the secondary coil divided by the current in the primary coil. Flux linked with the secondary coil divided by the current in the primary coil. Thus, we can write flux linked with the secondary coil as M into IP, or the induced EMF in the secondary coil is negative of rate of change of flux in the secondary coil, and we can write minus d by dt of. This is M into IP, and therefore I can write minus M into dIP divided by dt. So, mutual inductance is the induced EMF in the secondary coil divided by the rate of change of current in the primary coil. And again, just like self-inductance, this is the property of a pair of coils. This is the property of a pair of coils. Now, if we consider two coils wound in the same direction, for example, they are wound over each other, then the mutual inductance M is given by K root L1 L2. K root L1 L2, where K is a constant known as coefficient of coupling or coupling constant ranging from 0 to 1. If the coupling is complete, then the coefficient of coupling is 1. If there is no overlap of the fluxes, it is 0. In general, the net inductance is given by L is equal to L1 plus L2 plus or minus 2M, where plus is used if the coils are wound in the same direction, in same sense we'll call, and negative if the coils are wound in opposite sense, And remember, these are for series combination. And if they are connected in parallel, then net inductance is given by L1 L2 minus M square divided by L1 plus L2 plus or minus 2M, So this is what happens in the case of parallel combination of two inductors. Suppose we consider a solenoid, one of the important types of geometries here. The self-inductance of a solenoid is given by mu naught n square AL, or we can write as mu naught n square pi r square L, where n is the number of turns per unit length, and of course r is its radius and L is the length. So this is the expression for the solenoid, or say self-inductance of a solenoid. See, during the growth of current in a coil, the external agency has to do certain amount of work. For example, let us consider a coil, and in order to set up current in the circuit, external energy, external source or external agency has to do work. So this work done by the external agency gets converted into energy of the inductor. Suppose the self-inductance of a coil is L and the current established in the coil is I. Then the energy of the inductor, energy stored in the inductor, is given by half Li square. The energy stored in the inductor is given by half Li square. Likewise, the energy density in a coil is given by B square divided by 2 mu naught, where B is the magnetic field established and mu naught of course is the permeability of free space. One of the very important applications of all these concepts is that of LR circuits, inductor and resistor circuits. Let us consider an inductor, a resistor, and let's assume that you are going to establish current in the circuit. This is called as growth mode. E is the source EMF, L is the inductance, and R is the resistance. So upon closing the switch, there is a current, and the parameters for the circuit are given like this. The current in the circuit is given by E by R into 1 minus e to the power of minus R by L into T. Minus R by L into T. This E by R is nothing but the maximum possible current in the circuit. 1 minus this is nothing but tau. Tau is nothing but the time constant of the circuit, which is given by L by R. So during growth mode, the current in the circuit is given by this expression. And remember, time constant is L by R and the maximum current is E divided by R. Suppose I consider at t is equal to 0, in this case, the current in the circuit is 0. The current in the circuit is 0. That means at t is equal to 0, the inductor behaves as open circuit. And at t is equal to infinity, as t tends to infinity, the current becomes maximum, which is E by R, and the inductor behaves like a closed circuit or closed switch. Behaves like a closed circuit or closed switch. So if you plot a graph of I versus t, the nature of the graph is like this. It increases, and as t tends to infinity, it becomes I naught, that is E divided by R, current being 0 at t is equal to 0. Suppose such a circuit is now allowed to undergo decay. Means now the same circuit which was connected here, we had closed the key here. So let's assume that now the key is thrown to this position, and we are allowing it to undergo a decay. That means whatever energy was stored in the inductor is now decaying. Then for such a circuit, remember this is the circuit, this is not going to participate, this is a defunct part, and for such a circuit, the expression for the decay current is given by I naught into e power minus t divided by tau, or I naught into e power minus t divided by L by R. I naught is given by E divided by R. So here if you look at this circuit, at t is equal to 0, that means at the moment the circuit is opened, the key is opened, the current in the circuit is E divided by R, that's the maximum current. While as t tends to 0 or infinity, the current in the circuit becomes 0. So this behaves like an open switch or open circuit. This behaves like a closed circuit, or the switch which is closed, the switch which is open are represented like this. And if we plot a graph of I versus t, the nature of I versus t graph is of this form. So at t is equal to 0, this is I naught, remember it touches the axis, so at t is equal to 0, this is the behavior. As t tends to 0, this is the behavior of the circuit. So these are some basic ideas as far as electromagnetic induction is concerned. Now if you take, for example, a coil, and if you make that coil rotate in a uniform magnetic field, let's assume that this is the axis about which you make it rotate, there is an inward magnetic field assume, and you are making it rotate, undergo rotation, then the area vector associated with a magnetic field goes on rotating, and the EMF induced in the coil is given by E naught sine omega t. That means if you try to plot the graph of induced EMF versus time, then the nature of induced EMF versus time is graph is something like this. So the induced EMF is changing alternately, and this is what is called as alternating EMF, and the current due to an alternating EMF is known as alternating current. In order to analyze this, we consider some of important terminologies. Some important terminologies are like this. Number one, RMS current or RMS value. It may be due to current, it may be due to voltage, etc. And as the name suggests, it is root mean square. You take the data, square it, find the mean, and finally find the root. And in order to find out the RMS value is given like this. First of all, find the mean, find the square, find the mean. So how do I do that? It is given by the following thing: integral I square dt 0 to t divided by integral dt 0 to t. So this is to be put under root, because this first part gives you the average. So this is how you find the average. While one more quantity which is important for us is what is known as average current or average EMF or average value of the EMF. Though this is given by I average, which is given by integral I dt divided by integral dt from 0 to t. But remember, if I consider an EMF of this kind, then for this the average over full cycle turns out to be 0. So full cycle average is 0. Therefore, for most of our analysis, RMS current plays a very important role. And for sinusoidal voltage, which is represented by E is equal to E naught sine omega t, or many a times it is also written as V naught sine omega t, we have V average is equal to 2 V naught divided by pi. Remember, this is for a half cycle. This is half cycle value, not full cycle value. And V RMS is given by V naught divided by root 2. Remember, this is for full cycle. This is evaluated for half cycle. So full cycle value and half cycle values are given like this. Likewise, you can also write I average is equal to 2 I naught divided by pi, and I RMS is given by I naught divided by root 2, where I naught is the peak value. I can also write it like this: I naught sine omega t. So these are some important terminologies which are useful here. AC circuits. When we say AC circuits, it simply means you have connected a source of alternating EMF across maybe resistor, maybe capacitor, maybe inductor, maybe one at a time, maybe two at a time, maybe all the three at a time, maybe in series combination, maybe in parallel combination, or mixed combination. So it's basically finding the circuit parameters using alternating EMF. Suppose I consider, say, one at a time. First, let us consider one at a time. That means maybe a resistor or capacitor or inductor. So I have pure resistive circuit. you have a resistor and an alternating EMF connected across this. The EMF connected is given by E naught sin omega t, E is equal to E naught sin omega t. Then the current is given by I naught sin omega t, where I naught is equal to E naught divided by R, where R is the opposition to the circuit or say current. And its representation can be shown like this. Suppose I draw E versus T graph, this is E versus T graph, and probably I versus T graph is like this. Maybe the current is more or less, all depending on the ratio. So one thing that is very obvious here is the EMF and current are in phase. They are in phase. That means if I show the phasor representation, V is along this direction and the phasor for the current is also here. The phasor for the current is also here. If I consider a pure inductive circuit, in the case of a pure inductive circuit, you have an inductor across which an alternating EMF of E naught sin omega t is applied, and L is the inductance. And as a result, you get current as I naught sin omega t minus pi by 2. Current is given by I naught sin omega t minus pi by 2, where I naught is given by E naught divided by XL, where XL is what is called as inductive reactance given by 2 pi FL or omega L. 2 pi FL or omega L. So in this case, you notice that EMF leads the current by pi by 2. EMF leads the current by pi by 2. So if you plot a EMF versus time graph or general graph is something like this. EMF versus time graph is here and the current versus time graph is like this. The current is lagging. The current is lagging. EMF is leading. Likewise, we can consider a pure capacitive circuit. If I consider a pure capacitive circuit, capacitance C and an EMF of E is equal to E naught sin omega t is applied, then we get the current in the circuit as I naught sin omega t plus pi by 2, where I naught is E naught divided by XC, and this XC is known as capacitive reactance, which is equal to 1 by 2 pi Fc, or this is 1 by omega c. 1 by omega c. So a plot of EMF versus time graph is something like this, while the current versus time graph is, it is leading. So this is current versus time graph. And if I plot the phasor diagram, this is EMF and the current phasor is here. It is leading by pi by 2. Suppose I consider a series combination of inductor, capacitor and resistor. You have a resistor, an inductor and a capacitor all connected across a source of EMF. E is equal to E naught sin omega t. Resistance is R, inductance is L, capacitance is C. Then for such a circuit, the current is given by I naught. Now E is given by E naught sin omega t, and the current is given by I is equal to I naught sine omega t, say plus phi. If you consider such a case, the current is given by E naught divided by Z. First of all, current is given by E naught divided by Z, where Z is what is known as impedance of the circuit, which is nothing but the net opposition offered to the current, which is given by square root of R square plus XL minus XC whole square. XL minus XC whole square. This can also be represented like this. Suppose I show the triangular representation. This is your R, this is your XL minus XC, and this turns out to be Z, which is root of R square plus XL minus XC whole square. And this angle is phi. So you can write Z square is equal to R square plus XL minus XC square. If I multiply by I naught, I get I naught Z whole square is equal to I naught R whole square plus I naught XL minus I naught XC whole square. But this clearly is V naught, so I can write E naught is equal to, this is voltage across the resistor whole square plus VL minus VC, they are all peak values, remember, whole square. Thus, the voltage, the peak voltage across the entire setup is related to peak voltage across the resistor, and those across inductor and capacitor are connected like this. This is also represented like this. Tan phi is equal to, if you look at this triangle, impedance triangle, tan phi is given by XL minus XC divided by R, or this is also given by VL minus VC divided by VR. So any of these representations is perfectly fine. Suppose I consider the case in which XL is equal to XC. You notice that the impedance becomes R. This is in fact the minimum impedance possible. And if the impedance is minimum, obviously the current is maximum. This condition is known as resonance condition. So at resonance, the current in the circuit is maximum and XL and XC are equal to each other, and we can also say VL and VC are equal to each other. And thus, E naught is simply equal to VR. That means the entire voltage across the entire peak voltage across the source appears across the resistor. So a plot of impedance versus frequency graph is of this form. The impedance reaches its minimum value, so the graph is something like this. At resonance frequency omega naught is the nature of the graph. If I plot the current versus frequency graph, this is the nature of the graph. The current becomes maximum at that resonant frequency. And how to find out that resonant frequency? Fairly simple. As XL and XC are equal to each other, I can write omega naught L is equal to 1 by omega naught C, or omega naught is equal to 1 by root LC, or F naught is equal to 1 by 2 pi root LC. So the frequency at which the current in the circuit reaches its maximum value. These ideas can be used to represent the idea of the power dissipation in the circuit also. So how to represent the power dissipation? The power dissipation in the circuit is understood in terms of a quantity called as power factor. Power factor is given by cos phi, which is R by Z. Cos phi, which is known as power factor, which is given by R divided by Z. So now The power dissipated in a AC circuit can also be represented in the following form. The average power dissipated in the AC circuit is given by Vrms Irms into cos phi. This is represented in various other formats, of course. We know that Vrms can be written as V0 divided by root 2 and Irms can also be written as I0 divided by root 2, etc. So these are the other ways of representation of the power dissipation in the AC circuit. So one of the very important concepts that is worth mentioning at this point is the idea of wattless current. So what is wattless current? As the name suggests, the power dissipated is 0. When does the power dissipated become 0? When cos phi is 0 or phi is equal to pi by 2. For what circuits is it pi by 2 or where is it pi by 2? Obviously across inductor and capacitor. As the power dissipated across the inductor and capacitor are 0, remember power is dissipated only across the resistor, and such a current which dissipates 0 power across the inductor and capacitor is known as wattless current. Okay. Parallel LCR circuit. If we consider the three elements inductor, capacitor and resistor all connected in parallel across a source of EMF, E is equal to E0 sin omega t, then this circuit is identified by the following concept. The current in the circuit is given by I is equal to IL plus IC plus IR. So we can write this current as I is equal to V0 divided by Z into sin omega t. So this is a representation of a parallel LCR circuit. This can also be represented in a slightly different way. You can also think of another combination. Inductance and resistor are connected in series. Inductance and resistor are connected in series. And a capacitor is connected across this branch. For example, L and R and C. And across this, we connect a source, for example. Then, in this case, the resonance takes place for a frequency given by 1 by 2 pi square root of 1 by LC minus R square divided by L square. So, the resonance of this circuit takes place for the frequency which is mentioned here. The idea of choke coil is one of the very important ideas as far as wattless current is concerned. In a purely resistive circuit, the power loss is maximum because the power factor is given by cos phi is equal to R divided by Z. And this is nearly equal to 1 as phi is nearly equal to 0. Hence, we can avoid the use of resistance in AC circuits, and this helps in reduction of wastage of power. So, a choke coil is a coil which has high inductance and negligible resistance. Thus, the power factor is almost 0, and therefore, a choke coil controls the alternating current without any appreciable energy loss. There is no energy loss as far as a choke coil is concerned. One of the important applications of these concepts is the idea of transformers. In the case of a transformer, what do? You connect an input and an output across a metal frame like this. This is known as primary and this is known as secondary. This is basically AC input and this is basically AC output. And suppose V2 and Vs and Vp, I will write here Vp and Vs are the peak voltage across the primary and secondary, currents are Ip and Is, and number of turns is given by N primary and N secondary. Then for an ideal transformer, these are related simply like this: Vs divided by Vp is equal to Ns divided by Np, which is Ip divided by Is. So the relation connecting them is like this. And the efficiency of a transformer is given by output power divided by input power. Output power divided by input power, and of course multiplied by 100 to get it in terms of percentage efficiency. So these are some important concepts as far as EMI and AC is concerned. So go through these concepts one more time to have a good grip over the concept. In our next session, we will discuss numerical problems.